And hello everyone, Paul here to continue our adventure in plate tectonics. Okay, so remember from last time that plate tectonics is kind of the updated idea of continental drift, right? Continental drift was just the idea that it's the continents that are moving. Plate tectonics says no, right? It's not just the continents, it's the entire crust of the earth that's moving, which may or may not include a continent, right? For example, the Pacific plate, there's no continent. The Nazca plate, there's no continent. The Scotia plate, there's no continent. But yeah, the North American plate contains North America, the South American plate, South America, etc. And these are the units that move around. Remember, if we look at the distribution of volcanoes, we can see that they, more or less track with plate boundaries. They're at least near plate boundaries. Usually, Hawaii is a big exception that we'll talk about when we talk about volcanoes. But most volcanoes are at least near plate boundaries, right? Same thing with earthquakes. Um, every little red dot's an earthquake. This is probably about 3 or 4 months worth of earthquake. And once again, Hawaii is proving to be an exception, but most earthquakes are also happening along plate boundaries. You can see the Philippine plate outlined very well here. You can see the Nazca plate, the Cocos plate, the Pacific plate all around here, etc., etc. Right? And so yeah. So it seems like all the fun is happening at plate boundaries. So let's talk about those. So if I've got two tectonic plates, they can do three different things. They can move away from each other, they can move toward each other, or they can slide along past each other, right? So if they're moving away from each other, the word that we use for that is a divergent plate boundary. To diverge just means to move away from, and so when tectonic plates are moving away from each other, we call that a divergent boundary. This is Mount Kilimanjaro in Africa, which, as we will see, is on a divergent plate boundary. We've kind of already talked about divergent boundaries. These are mid-ocean ridges, right? And so if I pull up the map that we've been looking at of the Atlantic, right? So here, this mid-ocean ridge running up through here, running up into Iceland is all divergent plate boundary, right? This is moving that way, 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 right? And so yeah, so these plates are moving away from each other along this mid-ocean ridge. If we follow it right up here into Iceland, we can see that Iceland is exposed seafloor that is, kind of covered in volcanoes. There's a lot of volcanoes in Iceland, and that will be important. Well, that will come back here in just a few minutes, right? Same thing's happening in the Pacific, though. There's the East Pacific rise that comes up in here like this, okay, and then kind of around like this. So let me go back one slide. So Iceland here on the ground looks like that, right? And so this side is moving this way, and this side here is moving that way. And so this, I know we're looking north here, and so this side is geologically Europe and Asia. This side is geologically North America, and this is moving that way, and this is moving that way. If you build a bridge over this, you need to put it on rollers or something, because it's a few centimeters a year. It'll actually make a difference. You can also go scuba diving between the two tectonic plates, something that one of these days I'm going to do, y'all. But so once again, I don't know which is which here, but this is moving that way, and this is moving that way. There's another thing about divergent boundaries, though, and that is they tend to happen in groups of three. If we look at this map of plate boundaries, we can see, like for example, right here, that the Earth has broken apart and is splitting into 1, 2, 3 parts, right? 3 pieces. And when the Earth breaks apart like that, it just tends to break into 3 pieces, right? If we look around, we can see that, yeah, right, these things tend to come together or break apart in threes, and we call that a triple junction. And the most famous triple junction isn't even really on this map. The most famous one is right here between the Red Sea, the Gulf of Aden, and then the African Rift Valley running down through here. Here's a better picture of it. Um, and so we can see here that what's happening here is the Earth is splitting apart here. And so the Red Sea is one boundary. The Gulf of Aden represents another one. This would be the Arabian Peninsula, for our purposes, the Arabian tectonic plate, and it's kind of moving to the northeast. Meanwhile, though, Africa is breaking apart. This part of Africa is moving this way. Let me show you on Google Earth, because we can see a couple things here. First of all, the green line is the plate boundary. So you can see it running down the Red Sea, down the Gulf of Aden, and then you can see it running down where it kind of goes around Lake Victoria here. This area over here is sometimes called the Somali plate, because the country of Somalia is on it, along with a few others. But it gets a little complicated around Lake Victoria because it's kind of splitting around. But see these volcanoes running down through here? Right? Kilimanjaro is down here. If you look at the rest of Africa, you see some isolated volcanoes, but not like this, right? And so, this is kind of like Iceland, right? As Iceland spreads, you draw up magma and lava and make volcanoes, and as Africa is breaking and spreading apart here, you get the same thing, right? You get all these volcanoes running down through here. On the ground, it looks like that. That's what the Rift Valley looks like. It is a beautiful area, rich in history and paleontology, by the way. This part of Africa is where humanity comes from. It is from Eastern Africa that we left and spread out throughout the world. But the fossils of our oldest human ancestors we find in this part of Africa. This is quite literally where we come from. So that's divergent boundaries. Areas where plates are moving away from each other, you tend to get volcanoes, and you tend to get some shallow focus earthquakes. Now we also though have transform boundaries, and these are areas where one plate is sliding past another. And the reason I do these now is because there is a case in which these are related to divergent plate boundaries. Let's look up here just south of Iceland. And so just south of Iceland, we have, let me make sure I'm in drawing mode here. Let me make sure we're drawing. Okay, cool. So just south of Iceland, we have a divergent boundary here, right? We have tectonic plate moving this way. We have tectonic plate moving this way. Okay, but look here. Look right here, because where it's offset, right? It's offset there. And so over here we have tectonic plate moving this way and tectonic plate moving that way. Now let me redraw it over here so we get the idea. That's why I kind of put the picture where I did. So there's Iceland, and so coming down, we've got divergent boundary, right? This is moving this way. This is moving this way. Then it's offset, so it picks up again over here. And there we go. And this is moving this way. And this is moving that way. And my arrows. Okay. You get the idea. Now, and so once again, lots of volcanoes up here in Iceland, right? Lots of volcanoes there. But look right in between here. Right now, this is a plate boundary, right? I've got plate A over here. In this case, it's the North American plate. I've got plate B over here, which in this case, it's the Eurasian plate. So right here is a boundary between plate A and plate B. Okay, but look at what's happening, right? This plate B here is moving kind of to the south. Don't do that. Is moving here to the southeast. Plate A is moving to the northwest, right? And so they're grinding up against each other there, right? That's a recipe for earthquakes, right? And so this boundary here between plate A and plate B is set up by this offset of a divergent boundary where it goes here, then it jumps over here. And right in between there, you're going to get all kinds of seismic activity in between there. It's not going to be huge and it's not going to be deep, but you are going to get a lot of seismic activity in there. And one place this is happening that's kind of famous is out here in California, right? You've got the east, let me make it so I'm pointing again. There we go. You got the East Pacific Rise that comes up here into the Gulf of California, comes out again up here, makes a tiny little tectonic plate up here called the Juan de Fuca plate. Let me show you schematically, right? So this comes up. And so now this is being shoved northward, this is being shoved southward, but this is all being set up by divergent boundaries. It's a little more complicated than what we saw, but not much. And so, westernmost California, definitely from San Francisco southward, maybe a little bit further north southward even, you're not on the North American tectonic plate, right? You're on the Pacific plate, and you're moving northward relative to the rest of North America, and that's what makes the San Andreas Fault, with all kinds of earthquakes all along here. Not very deep and not very big usually, but most definitely it has them. Here's a block diagram from an earthquake. I forget which one this was. I don't remember. But anyway, Loma Prieta. This was a Loma Prieta earthquake. And so back in 1989. And but the reason that the earthquake isn't important, the year isn't even important. What I want to show you here is how this is the Pacific Plate, and it's getting shoved northward relative to the rest of North America. And you can see a couple things here. First of all, you can see arrows indicating the relative motion, but you can also see that it's not really as simple as one San Andreas fault, right? Here's the Hayward fault. There's the Calaveras fault zone. There's lots of faults out there in California. The Earth it's never going to be as simple as the Earth breaks in just, along one line. That's not going to work that way. Another way to do it though, right, is just shove one plate along another one, right? Here's the Caribbean plate down here. Here's the North American plate up here. It's moving this way. You can see the arrow here showing North American Caribbean, right? It's moving this way, and as it moves that way, it gets shoved along the top of, or the north side of, the Caribbean plate, making all these earthquakes here off of Puerto Rico. There's one in, God help them, Haiti. And that's why you're getting these earthquakes in Haiti especially. But because, it's a transformed plate boundary. You've got the North American plate sliding along top of the Caribbean plate. What's happening over here, though? Because this looks different, right? Look, we're picking up volcanoes over here, right? Not as many earthquakes. Every now and then you get one, but mostly volcanoes over here. Well, what's going on there? Well, this is a transformed plate boundary. This is a convergent plate boundary, where two plates are coming together. Okay, now to understand that, we want to go, let's take a kind of a typical area off the west coast of South America. You've got a plate out here called the Nazca plate that is just seafloor, and then you've got the South American plate over here, right? And so let's take a cut through it, and let's look at it from the side, and it's going to look like that. And so here's the trick. The oceans are where they are, and the continents are where they are, because they're made of different rock. Oceanic crust, we've kind of already seen oceanic crust. Remember Iceland, right? Oceanic crust is relatively thin, only about 10 kilometers thick. It is relatively dense, maybe 3.1 in density. Or 3 or 3.1, a little bit dense. And in terms of rock, it's basalt, which we'll talk about rocks later on, and you'll know a little more about that. But anyway, continental crust is thicker. Where oceanic crust is only about 10 kilometers thick, continental crust is 40 kilometers thick. It is relatively not dense, but it's not like you would pick up a piece of oceanic crust and pick up a piece of continental crust and feel the difference. It's not that great. But continental crust might be where oceanic crust is maybe 3 to 3.1, continental crust is maybe 2.9 to 3. Right, just a little bit less dense. And I know there's a lot of different kinds of rock here on the continent, but if you melt it all down and put it in a hopper and cool it, it's granite or something like granite, right? And so we have two different kinds of crust. If we look at this map, showing the thicknesses of the crust, we can really see the difference, right? Continental or oceanic crust, rather, is pretty universally about 10 kilometers thick, right? Where continental crust, sorry, I keep getting those confused, don't I? Where continental crust ranges, from 40 kilometers is kind of normal to more underneath mountains at 70, maybe less in extensional areas like 30, but 40. Okay, so two different kinds of crust. So if we have two different kinds of crust, we can bring them together in three different ways, right? We can bring continent up against ocean, we can bring ocean up against ocean, or we can bring continent up against continent, right? So if I have three different kinds of, if I have two different kinds of crust, there's three different combinations. And each is a little bit different. Let's start with continent ocean. Right, so with continent ocean, oceanic crust is going to meet continental crust. Okay, and we already looked off of the west coast of South America to see this when we were talking about the different kinds of crust. But now let's talk about what's actually going on out there. Okay, and so what's happening here is we have a divergent boundary here, right? And so magma is being drawn up here. And creating new rock there. This slab of rock here is moving this way, and because it is thinner and more dense, when it meets this continental crust, it goes down underneath it. Okay, and so what we get is we get earthquakes. Going down, getting deeper and deeper and deeper underneath this continental crust. This area here is called the Wadati-Benioff zone, and in a minute here I'll show you Google Earth earthquake plot showing how earthquakes get deeper and deeper under your feet as you walk back from the beach, from the plate boundary. The earthquakes get deeper and deeper, and that's why, because they're following that subducting plate down into the mantle. But eventually what happens is this subducting plate starts to melt. And as it melts, that magma will migrate its way upward, and then eventually, once it reaches the surface, you get volcanoes. Big ones. Nasty ones. Okay, these are not the happy little Hawaiian, let's go roast a pig on the beach and dance. No. These are runaway or die volcanoes. You do not want to be around when one of these erupts. And so this is what happens though as these ocean continent convergent plate boundaries. You get earthquakes, shallow to deep. As that oceanic crust gets pushed down, you get melting, rising magma, turning into lava when it breaches the ground surface and produces an earthquake. If we look off of the west coast of South America, we can see this, right? Here we can see earthquakes. You've got the little Nazca plate over here moving this way, getting shoved underneath South America. And you can see earthquakes getting shallower. Remember, the color coding here is depth. And so the orange is shallowest, and then yellow is deeper, green is deeper, and blue is deeper still, right? And we don't have any lined up really well here, but you get the idea that as you work your way inland, those earthquakes get deeper and deeper under your feet. And then also, right, I can kick in some volcanoes here, right? From that subducting plate melting and that magma rising up through the crust. We don't need to go all the way down to South America to see this, though. We can go over to our Pacific Northwest, Portland, Seattle, up here in, like I said, the northwestern portion of the United States, where you got a little tiny plate out there, the Juan de Fuca plate, getting pushed underneath North America. You're going to get earthquakes down like this, and then eventually you'll get melting and, of course, volcanoes on that backside. They are beautiful. Beautiful mountains and beautiful, beautiful volcanoes. There's Mount Hood. The Pacific Northwest really is just lovely. But every now and then it does that, right? Every now and then it blows up. This is Mount St. Helens, and so you want to visit, but you want to be careful too, because this definitely does happen. Same thing with the mountains in South America; they really are just beautiful. The Andes Mountains are lovely, but they are very explosive volcanoes. They really just are. Okay, so that's ocean continent, right? You get one piece of the Earth's crust sliding under the other one, and so you get earthquakes, shallow to deep, and then volcanoes from that melting and rising magma. What if I bring two pieces of oceanic crust together, right? That's the Caribbean. That's that western, or rather eastern Caribbean. Okay, so now I've got two pieces of oceanic crust. So both are thin, both are dense. But eventually one's going to go under the other. So one goes under the other. You get the same thing. You get earthquakes getting deeper and then melting down here and then rising magma. And now you get volcanoes at sea, right? Remember this? Right, remember this? So up here we got a transform boundary, but down here we've got an ocean convergent boundary producing these volcanoes and a few earthquakes. If we looked, I can show you a picture down here of St. Catherine. There it is. I know it doesn't really look like a volcano, but it is a heavily eroded one. But all these islands here are volcanoes. St. Martin here is marked because I did some work on an ancient volcano there, and so. It's just beautiful, but it is most definitely volcanic. We can also go over to the Pacific, to the Philippines. So the Philippine Islands down here. This is Japan. This is the tip of the Korean Peninsula here. Taiwan, China, and so the Philippines Sea here. And so right here, you've got these islands here that are formed from the Pacific plate out here getting pushed underneath the Philippine plate here. And I can show you one island in particular that's kind of famous here, Iwo Jima, right there. And here it is up close on Google Earth. And so this island is famous because there was a big battle here during World War II, and you have probably seen this picture of the Marines raising the flag on Mount Suribachi, which is a volcano on the southern side of that island. But all of those islands in through there are volcanic in nature, and so that's an ocean. Now, what about a continent convergent plate boundary? What if I bring together two pieces of continental crust? Well, if I do that, what's going to happen is you got two thick, not dense pieces of crust smacking into each other. Okay, and so the poster child for this is the subcontinent of India hitting Eurasia. And so, tens of millions of years ago, India was to the south of Eurasia, but moving northward very fast, very fast. And then what it's going to do is it's going to smack into Eurasia and throw up the Himalayan mountains. Now, this is something when we think about this, this is not something that happened a long time ago. This is something that is happening today. India is still moving northward about 5 centimeters per year. if we look at this on Google Earth, we can see India here. Let me get my pointer going again here. And there we are. We can see India here, and you can see the arrow. It is still moving northward, about 5 centimeters a year, about the same speed that North America is moving westward, throwing up the Himalaya Mountains here, the tallest mountain range in the world. And of course, there's Everest, the tallest peak in the world. Our Appalachian Mountains formed this way, right? When Africa, Europe, North America, and South America all collided with each other, right? Whenever you see mountains with no volcanoes, right, that's what's going on. If I look back here, I've got the volcanoes turned on here. There just aren't any. There's a little one there, but not associated with this plate boundary. Nothing is going down into the mantle and melting. It's all just hitting and going upward, right? So the Alps, the Pyrenees, our Appalachians, right? When you see mountain ranges that don't have volcanoes in them, this is one way or another how they formed. And so let's think a little bit, though, about what's moving these tectonic plates, right? I mean, we kind of jumped and said, okay, well, they're moving, and here's the different kind of boundaries. But now let's go back and ask ourselves, okay, what's moving them? Because remember, this was a problem that Alfred Wegener had, right? He felt like the continents were moving, but he didn't know what was moving them. And to be perfectly fair, to this day, we still don't really know what's moving them, but we have some ideas. We understand that the mantle of the earth is solid, but it will flow. Now, I know that's weird because we're not used to solids that flow, but I would ask you to think about Play-Doh, right? Play-Doh is solid. It's not a liquid or a gas. But if you squeeze it, it flows. If you heat it, it flows even better. Don't heat your Play-Doh, but you get the idea. And so the mantle of the earth is like that. And when we talk about earthquakes, we'll talk about how we know it's like that, because seismic waves travel through it, and there are certain seismic waves that only travel through solids. So it's solid, but it flows. We call that flow convection. And one way or another, that convection in the mantle is turning into movement. That movement in the mantle, that convective movement in the mantle, there I got it, is turning into movement of the Earth's crust. So how is this happening? Well, you've got this in your notes, but I'm going to jump back here and remember our kind of prototypical plate tectonic area here, where we can take a cut through the Nazca plate up onto the South American plate. Look at it from the south, and it looks like that. Okay, now let's use this to talk about how we're getting this Nazca plate to move, okay, or right. So let's think about that. Okay, so first of all, there is magma coming up here at the mid-ocean ridge. And it is applying some force, not a lot, not a whole lot, but it is applying some force to it. Let's call that force ridge push. Although I'm going to tell you right now, this is not too big a deal. We don't really think we're pushing a whole lot on the plate here. It is applying some, so it's on the list, but probably not a huge deal. Okay, and when we talk about earthquakes and faults, we'll talk kind of about how we know that. Over here, though, as this goes down into the mantle of the Earth, it's being pulled on. And we call that slab pull. And it turns out that might be a big deal. The Pacific plate is moving very quickly. The Pacific plate is also surrounded by this kind of convergent boundary where it's going down into the mantle. And there's a lot of people out there who think that those two things are related. That the plunging of the plate down into the mantle and that pulling that happens as a result of that is what's causing the Pacific plate to move so quickly. Another thing that's going on is it's downhill, right? If I think about this, from here to here is downhill. right? And so it might be just as simple as, especially with a smaller plate, that you just kick up one end of the plate and the whole thing just slides down. We call that ridge slide. And it gets particularly interesting when you realize that there's a layer underneath here called the asthenosphere that's frankly kind of slippery, and it'll make it a lot easier for this slab to slide downhill. And since it's sliding from a ridge, we call it ridge slide. And so that works really well for smaller plates. You're probably not going to move the Pacific plate that way, though, right? It's a very big plate with with a ridge on one side of it, but the ridge isn't that big relative to the rest of the plate. So what else? Well, there is that convection, right? That convection doesn't stop there, right? That convection comes up and moves along underneath the plate, kind of dragging it along, and so we call that basal drag as that convective cell moves along underneath the plate. This is the way most people kind of intuitively think that plates are moving. They're just like, yeah, but that would do it, wouldn't it? And a lot of times it likely is. I mean, I like to think of it when I think of basal drag. I think of a piece of plywood on a river, right? Something brittle and thin being carried downstream. Here's the problem. Let me draw. There are places where we know for a fact that the convection is moving one way, and this isn't the case with the Nazca plate, so don't be specific about that. But we know for a fact that the convection is moving one way and the plate's moving the opposite way. Or maybe not the same direction as the convection, but there are literally places where we know it's moving the opposite way. So yeah, right. I mean, it happens. It's going to happen. It's going to happen, but it can't be the only thing. It can't explain everything. In fact, none of these, especially these three, none of these by themselves explain everything. This one doesn't really explain much at all. Okay, but so it really might be that if you ask, what's moving a tectonic plate, the next question should really be which plate, right? It's very possible that smaller plates are being moved by ridge slide, where larger plates might be getting moved by slab pull and basal drag, or some combination. So it's complicated. It's very complicated. And as you might imagine, it's also very difficult to study. Okay, so there we are with plate tectonics, and so next up is minerals and rocks. So y'all take care, have a good day, and I will talk with you later on. Okay, bye-bye.